Hello, I'm Professor von Schmohawk, and welcome to YU. In our lectures so far, we have seen how numbers evolve from the primitive concept of natural counting numbers to whole numbers with the addition of the number 0, integers with the addition of negative numbers, and then rational numbers. Since rational numbers are closed under all four arithmetic operations, addition, subtraction, multiplication, and division, you might think that rational numbers finally represent a complete collection of numbers. We can add, subtract, multiply, and divide, and never have a problem representing the result. Yay! This is what the Greeks thought as well. That is, until they discovered an inconvenient truth: that there are certain types of quantities that cannot be represented by rational numbers. Nobody knows exactly who made this disturbing discovery. It may have been the great Greek mathematician Pythagoras, but legend has it was one of his students, who was subsequently killed for upsetting the apple cart with this discovery. Numbers were obviously a sensitive subject for the Pythagoreans. The proof of the existence of irrational numbers may have gone something like this. If rational numbers can represent any quantity, then they should be able to represent square roots. Now, the definition of rational numbers says that any rational number can be represented as the ratio of two integers. In other words, one integer which we will call p divided by another which we will call q. P over q is obviously a fraction, and like any fraction, we can write it in its simplest form so that the integers p and q have no common factors. We also know that since the square root of 2 is not an integer, the denominator q is some number other than 1. Now, since the square root of 2 and the quantity p over q are equal, then we can square them both and they will still be equal. The square root of 2 squared is 2, and the quantity p over q squared is p over q times p over q, or p times p over q times q. For this fraction to be equal to 2, we must somehow be able to reduce it to 2 over 1. But we already saw that q was not 1. So the only other way this fraction could be equal to 2 over 1 is to cancel out common factors in the numerator and the denominator. But we also said that p and q have no common factors. Therefore, there are no factors in the numerator that are the same as any factor in the denominator. So we can't cancel any factors, and there is no way that this fraction can be equal to 2. Therefore, this is an impossible situation. Our original assumption that the square root of 2 can be represented by the ratio of two integers must be wrong. The square root of 2 must be some value which is not a rational number. A number which is not rational is called an irrational number. This same argument can work for other square roots. For example, we can start with the square root of 3 and try and represent it as the ratio of two integers with no common factors. Squaring both sides, we get 3 equal to p times p over q times q, and since p and q have no common factors, this fraction can't be reduced to the integer 3. Therefore, the square root of 3 is irrational. This also works for roots other than square roots. For example, we can set the cube root of 2 equal to the same ratio with no common factors. Then cubing both sides, we get 2 equal to p times p times p over q times q times q, and since p and q have no common factors, the fraction can't be reduced to an integer, and so the cube root of 2 is also irrational. We saw in the chapter on converting fractions to decimal numbers that the rational numbers can be represented as decimal numbers which either repeat or terminate. A terminating decimal number has a finite number of digits after the decimal point, while a repeating decimal number ends with an infinitely repeating series of digits. The repeating sequence of digits can be as long as we like, but the number of digits which repeat is always finite. In other words, all repeating decimal numbers contain some finite number of digits which repeat infinitely many times. However, when we try and represent an irrational number as a decimal number, we find that the number will always contain an infinite sequence of non-repeating digits. No matter how many digits we write after the decimal point, the digits will never repeat. Therefore, we can never perfectly represent an irrational number either as a decimal number or as a fraction. With the invention of calculus, mathematicians were able to prove that numbers like pi and e are also irrational. In fact, there are an infinite number of irrational numbers. In the next lecture, we will see how mathematicians eventually combine the irrational numbers with the rational numbers to form the real numbers.